Good morning. We are reconvening now for the beginning of session 2, which is on particle dynamics and chemistry in the indoor environment. And to moderate this session is my colleague and good friend, Rich Corsi, sitting to my right. Rich.
Thank you, Bill. Well, welcome to session 2, Dynamics and Chemistry of Indoor Particles. I'll just say a few words before I introduce our speakers. This is a great workshop in many respects, but I think that the topics we're covering are challenging, complex, very important, and there exists a lot of research that still needs to be done to sort of sort out many of these things. But I wanted to point out that every one of the sessions, so that we're not too reductionist, every one of the sessions today connects with one another. And the session that I'm moderating sits right in the box that you see on the screen that says Transport, Fate, and Transformation, squarely between sources and exposure. And I've purposely shown the circle here around our session overlapping with exposure and sources. We know that the nature of sources and where they occur, whether they're floor or coming out of a supply diffuser, affects fate and dynamics of particles. The person being exposed by virtue of where they're located can affect fate and transport of particles in the indoor environment by their thermal plume, and individuals also affect the composition of indoor particles, as you'll see in our session. And I want to point out, particularly for Jeff Siegel, who will be speaking upon on particle dynamics, that mitigation strategies can have a huge impact on particle dynamics. So our three speakers, through various phone calls and emails, have tried very hard to craft a session that doesn't overlap too much with the other sessions. But I would keep in mind throughout this whole workshop that connections between these sessions and topics is very, very important. All right, so our speakers today have a lot of experience on this topic, and they're going to speak in a different order that's in your program. And I'll introduce first Jeff Siegel. Jeff's going to speak on dynamics of particle size and concentration indoors from a building science perspective. Jeff is a professor in the Department of Civil and Mineral Engineering at the University of Toronto, where he's been for a few years, but he was my colleague for 10 years at the University of Texas, and we miss him very much. Jeff, I'll let you take it from here.
Is there So what I'm going to need a microphone. Very important. I'll chain myself to the podium. So what I want to talk about today is how the building influences the particle size and concentration indoors. And you're going to see that there are, as Rich mentioned, lots of connections both within this session and to the broader workshop. And my job is made easier already by the first three presentations we saw. So when we think about what governs the topic of question, the size and dynamics of particle concentration indoors, it's of course because there are sources and sinks of particles indoors. But the point that I want to make is that the building is what's affecting or does affect many of those important source and sinks. So if we think about the framework that others have followed and that I'm going to follow here, spend just a few minutes on what we know and then move into emerging areas and finally knowledge gaps. We know a lot. We just heard about source characteristics, and I just did a very quick kind of crude literature review and said, what sources are there out there that we have more than 10 articles that publish an emission rate and a size distribution for various sources indoors? And of course, there are still many questions, as we saw, but there are many that are well described. And one, I had to cut out the picture, but we even know things like flaming fake Christmas trees, the size distribution of particles that are emitted from them. So just one example of this, cooking was mentioned in the first session. There is, although there are questions, there's still a lot of good work on cooking. So the plot on the right shows the, on the left shows the time evolution of particles emitted from a natural gas stove. under a particular set of cooking circumstances. And the table shows for different both gas and electric cooking sources with different properties of cooking going on, some information about the emission rate and the distribution of particles that are emitted. So again, there are questions, but we know something about some sources. On the sink side, there are many important sinks inside. 4 of them are shown here. And we've already seen, and I'm sure we'll see more kind of building as a box schematics here, but this one is mine because the stick figure is wearing a toque. And you can see that, you know, deposition, portable air cleaning, centralized air cleaning, and ventilation and leakage are all sinks that there has been a lot of research on. Still questions, but a lot of research. And just one example of this, and I'm not going to dwell on it because it's going to be covered later in the workshop, but for example, there's been a lot of work done on filtration. And we have size resolved filtration efficiency curves for many, many filters. We know many of the factors that influence those size resolved filtration efficiency curves. For example, the face velocity is shown in the work by Jim Hanley and colleagues. And more recently, we have work that shows filtration efficiency curves for much smaller particles, going down to the tens of nanometer scale or so. So filtration is another area where, again, questions, but we know a lot. So if I move into the area of emerging knowledge, when I think about things from a building perspective, I group things into 3 areas, and I'm going to touch on a 4th. Those 3 areas are the impact of building surfaces, the impact of HVAC systems, that's heating, ventilation, and air conditioning systems, and the heterogeneity of indoor concentrations. I'm not going to go into it in the interest of time and because it's going to be covered elsewhere. The impact of non-particle constituents on particle size and distribution, but I do want to mention that there are important. There are things like ozone that can lead to particle formation and other constituents in indoor air that can affect the size and concentration of indoor particles. So if we start with building surfaces, we all know that buildings have a lot of surface area, especially compared to something like an outdoor environment. We also know that there's a lot of very diverse surfaces in buildings. So even if you look around the room that you're currently in, you'll see probably some number of surfaces on the order of 100 or so that are easily visible to you. And to add to that complexity, indoor surfaces acquire chemical and biological patina that is linked to other things that are going on in the environment. And a point that's important to me and that I'm going to come back to a little bit later in the talk is that there's lots of surfaces that we don't see. And in fact, many of the most relevant surfaces we might not even be thinking about when we think about indoor surfaces. And the reason that surfaces are important, and we've already seen a little bit of this, is that surfaces do interact with particles in indoor environments in very meaningful ways. So some examples of some of the things that we know about surfaces. There has been theoretical treatment of relatively idealized particles and idealized surfaces from the perspective of deposition. There's been extensions of that work to more realistic environments with real building materials in them. There's been specific measurements of deposition to particular building materials. And so there is undoubtedly in these and many other articles that look at size resolved deposition to different indoor surfaces and surface materials. But the reason I put this in the emerging category was actually pointed out in the Thatcher and colleagues article, is that even though we know that surfaces have a big impact, it becomes very hard to actually predict something like a PM 2.5 deposition rate for an indoor environment. And that's been borne out by what we see in the literature. If we think about something like a PM 2.5 deposition rate, there are many articles in the literature that have either modeled or measured this, and you see variations for indoor PM 2.5 deposition rates that vary by approximately an order of magnitude or so. And so obviously there's still a lot of work to be done to bring some of the theoretical treatment to be able to actually understand what is different about one building from another. And one piece I would add to this is that I think one thing we have to get much more sophisticated in is our characterization of surfaces. Carpets span a huge definition of very, very different materials in terms of properties like their chemical composition, their surface roughness, and so on. And so that probably plays an important role in aerosol interactions as well. We heard a lot about resuspension, so I'm not going to spend a lot of time here, but we have measurements of different surfaces and of resuspension rates of particles of different sizes from those surfaces. We know something about surfaces and their interaction with airflow characteristics. And why I think this is an emerging area, and Brandon already touched on both of the points I want to make. One is that we're very often not dealing with a particle-surface interaction. We're dealing with a particle-particle interaction because there's a particle already on the surface. And Brandon led a nice review paper on that a few years ago. And then another article recently started to look in detail at the mechanisms that are leading particles to detach from surfaces on different materials. And I think that that's the kind of direction we need to think about in terms of what is affecting resuspension from the many different surfaces we see indoors. The second area of emerging interest is HVAC systems. And forced air systems are very common. Roughly all commercial buildings in the US have them. On the order of 3/4 or 80% of residential buildings in the US have them. Even in Canada, we see only about 2/3 of systems have them. And it's really a huge set of interactions we see between indoor particles and HVAC systems. So for example, if we have a filter in a central forced air system, how that filter works to remove particles is going to depend on how often the system runs and how much air goes through that filter. If we think about ventilation, obviously there's the amount of ventilation air, which is tied to directly to the HVAC system, but also the operation of ventilation system induces leakage, both in the ducts and in the building itself. There is also an impact on deposition and resuspension processes because of things like air turbulence and air velocities that are influenced by the HVAC system. The HVAC components can act as a source directly by emitting particles or as emitting precursors to particles like ozone. They can also act as a sink, and there's several articles on deposition to HVAC components in the literature. HVAC systems affect temperature and humidity and some of the environmental factors that affect chemistry indoors. And of course, they also serve to promote mixing in indoor environments. So really, if we want to understand indoor aerosols, we have to understand HVAC systems. And just to give an example of how far behind we are, one of my favorite HVAC parameters for residential systems is the runtime, how frequently the system runs. And to my knowledge, the 200 or so homes that are represented in the 3 articles here are the only homes that are in the literature where we've actually measured the runtime. So of the 80 or 90 million homes in the US that have central forced air systems, about 200 of them we've measured the runtime. Not only that, it's all in the southeastern United States. And not only that, some of these are relatively short-term studies, a few days, maybe as much as a week. And so we really know very little about this very important parameter. And the biggest study here by Kristen Setin and Attila Novoselats was for a year in 161 homes. It's a unusual sample in that these are high-performance, energy-efficient homes, generally speaking. But you can see that within that sample of homes, we see a huge variation of runtime between homes, but also across the year. So depending on what season you're in, this is Austin, Texas, so the air conditioning system runs much more in the summer than it does in the other seasons. So again, example of a parameter that's really important that we know, I would argue we know relatively little about. And just to show a little bit more specifically about how that might be important, this is a scaling analysis that shows the effectiveness of the filter, another parameter, Brent, that goes from 0 to 1. So the higher the better, for different filters for both PM 2.5 and PM 10 as a function of something called the recirculation rate, which is that runtime parameter times the flow rate divided by the volume. So it's kind of a normalized air change rate through the HVAC system. And two comments I want to make about this. One is that if our runtimes are quite short, and I'm going to show you some evidence a little bit later that in fact they might be, it doesn't matter what type of filter you have in place in the residence because air is not going through it. And similarly, if you don't have a very good filter, and by the way, the green is a MERV 7 filter, which is probably better than most homes have, it doesn't really, the runtime matters much less because, again, it doesn't matter if air is going through your filter if it's not removing particles of interest. So moving on to the third emerging area, the heterogeneity question, and Lynn already addressed this. We have this when we make exposure assessments to particulate matter or to anything, we usually make a well-mixed assumption for an indoor environment because that's the easy and mathematically tractable thing to do. But the same paper that Lynn showed, this is a smoker sitting different locations, exposed person sitting very close distances on a couch relative to a smoker. And you can see hugely different concentration distributions of what they're exposed to. So even over very short distances in the source, in the proximity of a source, you get very different exposures. This also happens on the sink side of the equation. So this is some work that Attila Novoselets and I did where we did some measurements and modeling, taking a couple of different portable air cleaners and putting them in different locations in a house relative to a source. And what you can see is that the effectiveness of the air cleaner is really important where it's placed in the house. And again, that's in some ways self-obvious, but also just shows the importance to which we might have to understand particle concentrations and their distribution within buildings when we want to assess exposure. And then the last point I'll make on heterogeneity says the same thing again. This is some work by Dongyan Rim and Attila Novoselets, where again they showed that you get very different exposure not just to particles, but to many indoor agents, depending on the proximity of the source, even very close distances of a source because of the complicated fluid mechanics that occur around the human being really can affect the exposure that occurs. So if we move from emerging areas into knowledge gaps, I want to make kind of one central point here, and that is our knowledge of buildings is really insufficient to understand our exposure to particles indoors. And I'm going to divide this into a few different knowledge gaps. The first one comes back to HVAC systems. So I mentioned the runtime issue earlier. This is the same plot, but with a few measurements of runtime, both from some of the studies I showed you, as well as from the gray literature. And you can see that runtimes can, in fact, be quite small. That's the horizontal lines here. And they can be larger. But the point I want to make is that if we look at how people have modeled runtimes and this effective recirculation rate parameter in the literature, we're tending to assume much higher recirculation rates than actually occur in buildings. And so I think that that's a very important point and points to the fact that if we're going to be talking about mitigation, we have to consider the HVAC system. The second knowledge gap I want to talk about is on ventilation dynamics. And so we have, we know that buildings have an air exchange rate. It's been discussed several times. But what hasn't been discussed yet is just how variable that air exchange rate is. So this is some work by Stuart Batterman's group, and this is a signal processing approach to look at air exchange rate in an unoccupied apartment. So this includes no occupant effects. This is a low-rise multifamily building in Brazil. where these data come from. And you can see that the air exchange rate varies by a factor of 4 or more over the course of week that they took the measurement. So this isn't even a big seasonal change, a big HVAC operation change. This is over a very short period of time with no occupant intervention, and we still see big variations in the air exchange rate. And I think that that's an area where we need to get a much better handle on the drivers that are influencing this. The third knowledge gap has to do with, again, we think of sinks as being very static in buildings, and they're not. This is some data from Matti Lehtomäki and colleagues from a building in Finland, and this is the filter efficiency curve for a filter from when it's installed at the top in the black squares to over 9 months of operation. And you can see that its efficiency really declines over time. And this is a well-known phenomena from the perspective of identification. That is, there are a lot of filters in the US marketplace that remove particles, at least partially, by an electrostatic charge applied to the filter. And that charge either is masked or decays over time, and the filter becomes less efficient over time. And so even though this is well identified, and numbers vary, but it's, let's say, approximately half of the US filtration market that have filters that might behave like this, we really don't understand what's causing this and why the decline is huge in some buildings and much less big in other buildings. And we're just starting to get a glimmer of that. This is some work from James Montgomery and colleagues that came out last year, where they looked at some of the changes in efficiency and pressure drop that happen on filters as a function of what they're being loaded with and the particular structures that are occurring on the filter as they load. And so I think this kind of fundamental research that lets us understand how our sinks behave is also really important. The fourth and final knowledge gap I want to address is what I call unseen surfaces and spaces. So buildings are not just the rooms we inhabit, of course. There's a lot of other spaces that we don't see. So those of you who are in this room right now, if you look up, there's a drop ceiling above our heads. And that communicates very well with the space that we're in. There's other kinds of interstitial spaces in walls and floors. In residences, we often have attics, crawl spaces, basements, knee wall spaces, all of which communicate well with the space and are essentially unknown from the perspective of either sources of particles or how they affect our exposure to outdoor particles. And I'll highlight garages at the end here. Garages are by far the most well-studied buffer space. There are many articles in the literature on transport of pollutants from attached garages to homes. Yet, if you look at those articles, to my knowledge, only one of them measured particles. And so even though we know these spaces can be important and can be important from an exposure perspective, they're largely unstudied. And so what I want to finish up with here is one way that we might address these knowledge gaps. And I'm going to use recent Canadian political history as a model here. And so until last fall, the past 9 years in Canada were a period of especially scientific darkness from a government perspective and a lack of data because of the administration that was in power. And then this past fall, we elected this gentleman here. And one of the first things, in fact, this was the very first policy announcement that came out of the government the day after the election, was the long-form census, which had been abandoned by the previous administration and led to a real lack of data, was reinstated. And, you know, there are rare times when I'm proud of my country, and this is one of them. And what I think we need to do is take that model and think about a really long-form building census. And so the idea here is that there is many things about the building that influence aerosol transport, aerosol exposure indoors, and we really need to measure those and understand those so that we can be effective in mitigation. And as a parting point here, I mean, some of this obviously is done by scientists, but this is also an opportunity for things like citizen science and practitioner science. There's lots of people who are in buildings for many purposes over the day that could help us in gathering some of this data. And I think that that would advance a lot of the questions we have about indoor aerosols by doing so. So thank you.